Hello and welcome to Rapid Tech, the show that brings you motorsport technology as you've never seen it before. Our unique 3D animations, drawings and images, interviews, and even a look inside the garage of one Craig Scarborough. Rapid Tech has it all. And in this episode, we'll be looking at one of the most important elements of any race car in any field, the front upright. We'll also be looking at 3Ds of the Mahindra Formula E car. Julia Piquet brings us a glossary of motorsport. We look back at the groundbreaking 1990 Tyrrell 018 Formula One car, and we're meeting one of the most indispensable figures of any pit lane or service area. Let's start though with our 3D animations. I'm with Craig Scarborough. Craig, Mahindra have caused quite a stir in Formula E this year, particularly with Felix Rosenqvist being as fiery as he is. But of course, there's a lot of technology behind it. Let's talk through what we've done now with these 3D animations.
So, over the first 4 seasons of Formula E, the cars have changed quite a bit in terms of the powertrain and the steering wheel. So, let's have a look at our 3D animations and see exactly how these have changed. So, in the first season of Formula E, they had a spec steering wheel. Everyone had exactly the same steering wheel, and this was made by the French company XAP. And it was a very simple, straightforward setup. You also used in Formula 2 and other categories of motorsport. And the controls in it were fairly simple. Back in season 1, every team ran a 5-speed gearbox. So what you had on the front of the steering wheel was 3 controls, 3 dials, which controlled the regenerative braking, the paddle settings on the back of the steering wheel, and also the torque from the motor. You had a dash display, a fairly simple low-resolution colour display, which had about 2 or 3 pages for each driver and some pages for the team to look at all the systems on the car. And you just had a few buttons really just to control neutral, radio, reverse, pit lane speed limiter, simple stuff like that. So there wasn't much the driver really had to do with the front of the steering wheel. But because this is an electric racing car, when we flick around now and have a look at the back of the steering wheel, the requirements are ever so slightly different. Season 1 and mainly in Season 2, most of the drivers had a multi-ratio gearbox, so they still had the up and down shift paddles on the back of the steering wheel. But there's no requirement for a clutch on a Formula E car. There's no clutch paddle therefore. So what you have is 2 extra paddles. You have this lower paddle on the back of the steering wheel, and what this does is controls the regenerative braking. So as the driver's going into the corner, they can pull on this paddle to increase the amount of regenerative braking, which therefore has an effect on the braking of the rear wheels. So this was very much used for the drivers to balance the car on the way into the corners in a way that you don't have to do, or you cannot do, with a petrol engine. Even though you do have engine braking with the electric motor, you can actually change that level of engine braking by playing with this paddle. And then the other paddle you have is on the top side, which is what we call the fan boost button. So fan boost was the means for Formula E for the fans to vote for their favourite driver, would give them a boost of power during the race. And the driver will pull this paddle in order to get the fan boost, extra boost of power. But equally for the drivers that didn't get fan boost, this would still be an overtaking button. So if there was in a lower power mode, pulling this paddle would bring you up to the maximum permissible power to allow the driver to make a manoeuvre for an overtake. So that was the steering wheel for Season 1 and Season 2. For Season 3 and 4 has come a new steering wheel with far more options. So let's now have a look and see the setup on there. So immediately you can see that there are far more buttons and dials on this steering wheel compared with the initial one. So first of all, you've got the same 3 rotary dials at the bottom, but additionally 2 thumb wheel rotaries on the top of the steering wheel for the driver. And now, rather than these being fixed by the regulation, the teams can choose whatever they want for these rotaries. So it will control things like how they do lift and coast, how they have the regenerative braking, playing with the differential, plus the pedal and the paddle and the torque maps, all controlled from here. Again, far more buttons around the steering wheel as well. Again, all customizable for however the driver wants them to work. And then the key thing was the new display. This display now has got much higher resolution screen, and there's more options for custom pages. So each team, each driver can have exactly the information they want on the dash display, which has really opened up the ability for the driver and the team to get information during the race on what's happening with the cars. Because we have to remember, Formula E doesn't have pit-to-car communication for data, it's only radio. So it's only the driver while racing the car that actually gets the information about what's going on with the car. So when we flip the steering wheel round and have a look at the paddle setup, you can see that the paddles have now gone up from 4 to 6 paddles, and again, completely customizable. So by the time we've now reached Season 4, the majority of the teams don't run gears on their cars. It's a fixed gear. They have no need for changing gears with the paddle system. So what you have is the driver will set up the paddles to suit how they like to race. So again, you'll still have the variable braking setup where the regenerative braking is adjusted by pulling a paddle, and that again, as I say, will change the balance into the corner as the braking on the rear axle increases or decreasing with the regenerative braking. Equally, the drivers will lift and coast at the end of the straight, and how they do that and the level of engine braking or the level of engine coasting during this period, again, is fixed by paddles here, and the drivers will choose tactically during the race whether they want to recover a little bit of energy or just have the car completely freewheel as they go towards a corner. Again, this is all very unique to electric racing. None of this sort of thing you would tend to get on a petrol-engined race car.
Now let's not allow the motorsport tech vernacular to get away from us. So who better than Julia Piquet, daughter of Nelson, to talk us through a glossary? Let's start with, hey.
Thank you, Peter. Well, let's get right into it. A is for aero. Aero is probably the most influential factor in Formula One at the moment. But it's not that aero is the most important aspect of a car's performance, but it is the one most open to teams' development. Tires, weight, electronic aids, and to an extent engines are fixed by regulation and therefore out of the team's control. Now, when we talk about aero in Formula One, what we really mean is downforce. Downforce is a vertical load put through the tires by the shaped bodywork around the car. The more load the bodywork puts through the tires, the more grip they will give. Downforce is different to weight, which also puts a vertical force into the tires, but on the car, weight will also try to slow the car accelerating or braking and will try to push the tire sideways when cornering. Downforce doesn't have these downsides. Downforce doubles with speed. A typical Formula One car will produce its own weight in downforce at around 100 miles per hour. However, downforce inevitably comes with a downside: drag. Drag is another force acting on the car, but along the line of the car and not vertically. Drag is produced in many ways due to the action of the air passing around the obstruction of the car. Drag has the effect of slowing the car along the straights. Drag increases with speed. At top speed, much of the engine power is spent purely overcoming drag. So ideally, teams want lots of downforce and little drag. That way they can get the grip in the corners and speed on the straights. This ratio of downforce to drag is termed aerodynamic efficiency. For a modern Formula One car, 60% of the downforce comes from the underfloor, with the front and rear wings contributing 20% each to the car's grip. The open wheels and rear wing are the biggest factors of drag created by the car. Thus, the underfloor, often simplified to the term diffuser, creates a lot of downforce and very little drag. Teams will try everything to make the airflow feed the diffuser to gain efficient downforce. Conversely, the rear wing is very inefficient, so teams will try to direct clean air to it to make it run as well as possible in order to reduce its angle of attack, and therefore the drag it creates.
Stay tuned for more with Julia as she tackles B for braking and C for cooling. Next up, we're joined by Ken Rumbold of MRTC, one of the most significant builders and suppliers of radio systems to the world of motorsport. Ken, thanks for joining us. Now, we kind of take pit-to-car radio systems for granted these days, but without question, there's a lot of science and probably a lot of trial and error involved. Let's begin by talking about the extent of your business right now and how near you think you are to perfection.
Okay, well, I think the simple statement is there is never perfection. It's in any activity, motorsport especially, everybody's striving for an advantage, some new innovation. But essentially, we just have to keep on with proven technologies as well as trying to move forward with stuff that appears with more modern techniques. Unfortunately, the development of electronic products that are suitable for our environment are probably not as rapid as the consumer products, because we're always looking for, shall we say, something that's going to be in a mission-critical environment. So all the latest technology of smartphones and things like this is lovely, but because it's out of our control when we're at an event, we can't always use it.
Ken, what have been the most significant development steps over the past 30 years or so in radios? I'm assuming that the general reduction in engine noise across the entire sphere of motorsport must be a big advantage.
Yeah, but the unfortunate thing is that engine noise isn't the be-all and end-all, because obviously the exhaust is behind the driver. So most of the noise comes from sort of general noise in the cockpit and wind noise. And depending on the aerodynamics of a lot of the cars, this is just as much noise as with a very loud engine. And obviously in closed cockpit cars, in touring cars and that sort of thing, these days, suddenly you'll find that the driver gets too hot in the car, so there'll be an enormous fan system put in the car, which we've got to fight against with our microphones, things like this.
Ken, it's sometimes very hard to hear the radio messages broadcast on TV, and yet the engineers on the pit wall seem to have no problem at all understanding what the driver's saying. Is that because they're actually receiving a different signal?
No, they get exactly the same as you hear on TV, but how can I put it politely? They're used to it. It's natural, once you're dealing with a type of audio for a long time, you're able to filter the noises. And so you're able to detect stuff more easily than an average person just listening on TV. The other thing, of course, is that the message from the driver is predictable. So they know, shall we say, they know what the message is likely to be, so they don't need to hear clearly every single word to know what the message is.
How many radios does a typical Formula One team run these days?
It varies with the, shall we say, with the regulations, but I would say probably for the basic team, probably 120 radios in F1 team. If you go outside F1 and look at something like Le Mans sports cars, I mean, a manufacturer team in sports cars will probably use more than 200 radios just for the engineering side, and probably another 100 or so for their hospitality, security, that side of things.
You're presumably privy to quite a lot of team chat that you're not supposed to hear?
No, is the polite answer. I only share secrets that everybody knows. So yeah, I mean, when we're working with so many teams, it's just taking information and gradually working out how much of it is top secret and how much of it can be shared. But I think the thing about our business is, to say, because we're dealing with so many teams, if we spread one secret, then we're finished. We're out of business. It's very simple.
Let's get straight into the next letter in our glossary of motorsport with Julia Piquet. B is for brakes.
B is for brakes. Mechanically, the brakes on a Formula One car are very similar to those on any road car. The driver operates a pedal that acts on master cylinders to pressurize brake fluid. That is then directed to brake calipers on all four wheels. When they are part of a high-tech racing machine, however, the Formula One brakes become very different to those of road cars in the detail. Formula One brakes can generate over 5G in stopping effect, slowing the car from 200 miles per hour down to 75 miles per hour in just 100 meters. This all starts at the driver's brake pedal. Its shape and leverage effect on the master cylinders is tailored to suit each driver depending on how they want the brakes to work and feel. There is one master cylinder for the front brakes and one for the rear brakes. Adjustment at the pedal allows for different ratios of braking effort between the front and rear brakes, and drivers will adjust this throughout the lap to get the ideal brake bias for each corner. Inside each wheel there is a brake caliper and brake disc, or rotor. F1 calipers are limited to being made from aluminum and use just 6 pistons inside each caliper. These push the brake pad onto the disc, and the friction between the two creates the braking force to slow the car. Unlike most road cars, the brakes aren't made from steel, but from carbon fiber. This material isn't chosen for its friction properties, as steel discs can break equally as well, but for its weight and thermal properties. Carbon brakes are incredibly light compared to steel. Each weighs just 1.2 kilograms and can operate at over 1,000 degrees Celsius or 1,830 degrees Fahrenheit. They also cost several $1,000s more. Although carbon brakes can run very hot, they must be kept in the correct operating window. Too hot and they oxidize and wear out too quickly. Too cold and they don't grip. Teams will carefully design ductwork to feed the right amount of cooling to the brakes for each track. cooling air passes around the caliper and also passes through holes in the brake disc. The number of these disc holes has increased over the years from 100 10 years ago to around 1,500 on the current cars.
Thanks, Julia. Now, Scarbs, you've brought us a nice front upright from your, I'll say workshop, sounds better than garage. I'm sure it is a beautiful workshop that you have there. So what and when, and what's the relationship between that and a 2018 front upright?
So this is a Renault 2009 front upright. So this sits inside.
How did you get that?
This was on an online auction. I won't name names. So this is a front right upright from a 2009 Renault, which is an R29, which was a big rule change.
So I can see a bit of carbon on the side there.
So yeah, so you've got some pockets for lightness,
right,
that have just been covered over with some carbon fibre, so the air flows around and into
right,
the brakes that much more effectively. So to kind of give you a feel for where this sits. So again, if we flick it round, this is front right tyre. So the brake disc and its bell mounts on here. You've got the thread for the wheel nut goes there, so the whole wheel goes over the entire assembly. Then you have your lower wishbone, your upper wishbone, and the steering track rod goes in there. These are all adjusted by little shims that go into these elongated holes.
Quite beefy, isn't it, when you see it up close?
It's a big, heavy piece, and I mean, while it's only sort of a couple of kilos, it is fairly substantial for when you see Formula One bits, which are normally feather light. And what you have, the body of this is machined aluminium from a solid block. By then, the regulations had fixed it to be aluminium. Before that, teams were using titanium. Some of them were using MMC. That was one of the reasons that aluminium was banned. Before that, they used to be made out of steel or sheet titanium, and they'd have been fabricated, meticulously by welding. But by this stage, these are now solid aluminium uprights, and then the axle that sits inside is titanium. And again,
interesting. Do that again. I mean, how much friction is there in that axle?
The surprising thing, you would have thought it would be really important that the axle spins very freely, but you can actually see there is friction here.
Why?
And the reason is this is under so much load in corners that they preload the bearings. So all of this clamping set up on the outside here squeezes the bearings tight so that there's no slop and play when you get the really high loads through cornering. You can imagine this obviously with 5 or 6G cornering or braking. There's a huge amount of load that's going through this. So they preload the bearings and you just don't get that kind of free spinning like you'd get maybe perhaps on a bicycle or a skateboard wheel. And then obviously you've got where the brake attaches as well, which is always, I think, one of the sort of unusual things. This is now underneath of the upright. And the brake just attaches with 2 very small, M8, M10 bolts.
Nice.
By regulation, these are fixed. You can only have 2 bolts and of a certain size. So if you think of all that braking effort going through here and you've just got some rather minuscule, I mean, my road car has bigger bolts than this.
And what about the ducting?
So what would happen now is, if we flick it round to the right way around, so this would be on the interface of the wheel, and this would be completely covered in the caked-in carbon fibre covers, and then there'd be lots of dedicated ducts running alongside here to feed the brake disc, but also to feed the caliper. So there'd be dedicated ducts going down to the pistons for the caliper, both on the inside and on the outside. And modern Formula One uprights will potentially also have the blown axle effect. So the back area here will be open and there'll be ducting air in.
So that's one of the areas where it would be different. But they're still machined out of solid that way, and they basically still look like that.
Yeah, I mean, you would, this wouldn't look out of place on a current Formula One car in terms of the design.
In 1990, a Tyrrell team already known for such innovations as the airbox, full-width nose and 6 wheels, surprised the paddock with its raised nose design. The car was conceived under the technical directorship of Dr. Harvey Postlethwaite, a designer who understood the trade-offs engendered by performance, did that extremely well. With a customer Ford V8 engine and relatively small budget, however, Harvey knew that he couldn't outgun the top teams just with engine power. So the next step obviously was going to be aero. And that's where the team's aerodynamicist Jean-Claude Migiot came in, and he came in with a radical new idea. Yeah, I remember that car well, Scott. I was actually working for Ferrari at that time, running their operation in England with Nigel Mansell and Alan Prost, good team. But meanwhile, down the back, no, they were really good, Tyrrell, that year. I mean, of course, with the 018, Jean Alesi and the Phoenix Grand Prix with that and Senna, I mean, that was, and Pirelli's, and Pirelli were a major part of that. But then the 019 with this interesting nose appeared at the Monaco Grand Prix, and guess what? Jean was brilliant again. that weekend. So that's the nose. The nose is what I think you,
It's the
you love
nose,
about that
yeah,
car.
I mean, this is the car that set the fashion for high noses, and that extends now to all of Formula One, most single seaters, even LMP1 endurance cars at Le Mans. The Audi has a high nose, so it's a concept that's really carried over, and it was something people were playing with in the years before, like you say, with the 018, which was a fantastic car, but equally the Arrows, the Leighton House Marches. Everyone then was trying to do something more with the front wing, which had always been split by the nose cone. So what people had started to do was to actually remove the nose cone under the wing and maybe just raise a bit of the chassis, but no one had really kind of gone full bore with that concept. And it was Jean-Claude Migeot that really came up with the big change in this concept. And I heard the story that he'd been away on holiday and was kind of doodling and sketching and conceptualising a car that had a completely round cross-section, almost forgetting about the requirement for side pods and what have you. And when he came back, they put some aspect of that into the wind tunnel, and that's why you get this almost conical nose of the Tyrrell 019, which was really the start of it, and that's where they started then to find some of the aerodynamic advantages in this high nose setup.
What about the anhedral aspect of it?
Dr. Harvey Postlethwaite, technical director at the time, if anyone else had gone, in an aero department, had gone to the technical directors, I want to raise the whole front of the car, 5-10 inches off the ground, the designer said, no, central gravity is way too important. But Postlethwaite understood that the gains in aero would offset the losses from the centre of gravity, and that's what happened. So when we look at the car, we've got an illustration of the standard car here. When you take the nose off, you can then see how high the footwell area of the car is and how the suspension had to be repositioned and just how much space there is underneath this area down to the ground, which was a quantum leap for anybody else, because every other car used to be completely flat from all the way under the car, all the way under the driver's feet, and often to the very tip of the nose, which would be absolutely flat to the base of the car.
That's it for this week's show. Thanks for watching, and let's end with more from Julia. We're at C now, C for cooling.
And C is for cooling. While traveling at almost unimaginable speeds around road courses and street circuits, a Formula One car also gets very hot. Most of the heat is generated by the power unit, that is, the V6 engine, its turbo, and its hybrid system. Although the gearbox, hydraulics, and electronics also require cooling as well. Without adequate cooling, the power unit would blow up, so cooling at the correct level is therefore critical. Too much cooling has its own issues because the power unit needs to be warm to run, but an oversized cooling system adds weight and aerodynamic drag to the car, so there is a fine balance to be found. The V6 engine is primarily cooled by a water coolant. The cylinders and heads are surrounded by a water jacket, and water is passed through this by a mechanical pump driven by the engine. This then passes into a radiator into the side pod to be cooled by the air passing through the car. The water radiator will be one of the largest cooling elements in the side pod. The engine also uses lubricating oil as a coolant for the reciprocating parts. As the oil leaves the engine, it is passed through a cooler in the side pod before being returned to the oil tank. Next, the turbo. The turbo is cooled by the same oil as the engine, but the air compressed by the turbo that will go into the combustion process is heated as it is pressurized. To maximize horsepower, this heated air will need to be cooled, and so it passes through a special type of radiator known as an intercooler. Although the hybrid system doesn't have the heat from combustion to warm it up, the electricity cycling between the battery and the motors via the electronics creates a lot of heat. Because of the fire risk, if the battery or electronics becomes too hot, the systems will shut down before overheating. All of these three elements of the hybrid system also need cooling. They will have separate cooling systems for the battery and then one for the motors with their control electronics. And due to the risk of leaks around the high voltage electrics, a special type of oil is used rather than a water-based coolant.